안녕하십니까. 성균관대학교 화학과의 김영독 교수입니다. 물리화학 실험 2 첫 번째 강의를 시작을 하도록 하겠습니다. 우리 물리화학 실험 2에는 총 5가지의 실험이 있습니다. 그래서 이 총 5가지 실험을 여러분들이 궁극적으로는 실험실에 와서 수행을 하시면 되는데, 특히 처음 5주 동안은 대면 수업을 하는 것이 아니라 이제 온라인 수업이 진행이 됩니다. 제가 아이캠퍼스에 매 주차에 대해서 강의 영상 하나씩을 업로드를 해 드릴 건데, 각 강의 영상에는 각 실험의 기초 이론과 실험 방법 그리고 결과 처리에 대해서 제가 소개를 해 드릴 것입니다. 그래서 처음 5주 동안에는 이 5개의 실험에 대해서 우리가 미리 온라인으로 공부를 하는 그런 시간을 갖게 될 것입니다. 그리고 6주 차에는 뭐 조편성이라든지 각 조의 그 실제 대면 실험 스케줄이라든지, 또 우리가 평가를 어떻게 하게 되는지, 출석에 대한 평가는 어떻게 하게 되는지, 그리고 여러분들 레포트는 언제까지 어떻게 제출을 하셔야 되고, 그 평가는 우리가 어떻게 할 것인지 등등에 대해서 소개를 드리는, 그러니까 학기 중간 이후의 강의 운영에 대해서 소개드리는 영상을 6주 차에 이제 올려드리게 될 것이고, 어, 그리고 이제 그 이후에 여러분들이 직접 실험실에 오셔서 실험을 하시면 되겠죠. 그래서 처음 6주차까지 온라인 강의는 여러분들이 10월 초 내지는 중순까지는 시청을 이제 완료를 하셔야 되는데, 정확하게 언제까지 이 온라인 강의들을 다 시청을 완료하셔야 되는지에 대해서는 또 따로 공지를 드리도록 하겠습니다. 근데 그 주어진 시간 안에 이 온라인 강의들이 시청이 다 제대로 안 되어 있으면은 이 시청이 안 된 강의 수만큼 또 결석 처리가 되기 때문에 온라인 강의도 주어진 시간까지 다 시청을 완료를 해주시면 좋겠습니다. 아무래도 제일 중요한 것은 여러분들이 실험을 안전하게 잘 수행을 하는 것이고, 또 실험을 안전하게 잘 수행을 해서 실험 데이터, 소위 말하는 이제 로우 데이터, 우리가 로우 데이터라고 많이 표현을 하는데, 로우 데이터는 그냥 실험에서 바로 얻은 그 데이터 값들이 되겠죠. 근데 로우 데이터만 그냥 얻었다고 해가지고 이제 실험이 이제 끝나는 게 아니라, 이 로우 데이터들을 수학적인 기법을 통해서 잘 정리를 해서 궁극적으로는 우리가 어, 물리적으로 의미가 있는 그런 값들을 얻어내야 되겠죠. 이제 그 과정들에 대해서까지 실험을 어떻게 하면은 잘 할 수 있는지, 그리고 실험을 한 다음에 어떤 데이터가 얻어지면 그 데이터 처리를 어떻게 해야 우리가 물리적인 의미 있는 값들을 얻어낼 수 있는지에 대해서 모두 제가 이 온라인 강의에서 설명을 드릴 것이기 때문에, 이제 온라인 강의를 꼼꼼하게 시청을 잘 해주셔야 여러분들이 실험도 잘 할 수 있고, 또 레포트도 잘 써서 좋은 학점을 궁극적으로는 받으실 수가 있겠죠. 온라인 강의에서부터 좀 신경 써서 들어주시면 좋겠다, 그런 말씀을 드립니다. 자, 그 다음에 이 강의가 이제 국제어 강의다라는 것도 좀 짚고 넘어가야 될 것 같습니다. 국제어 강의라고 해서 여러분들이 이제 실제 실험실에 와서 이제 그 조원들끼리 한 조에 아마 뭐 서너 명 이렇게 될 것 같고, 서너 명이 같이 이제 같은 실험을 서로 소통을 하면서 수행을 하게 되겠죠. 근데 여러분들이 실험을 하시는 동안에 뭐 이 국제어 강의니까는 무조건 실험실 안에서는 영어만 써야 된다, 뭐 이렇게 할 수는 없는 노릇입니다. 이제 실험실 안에서는 여러분들이 소통은 뭐 자유롭게 여러분들이 가장 편한 언어를 가지고 하시면 될 것 같은데, 근데 그래도 이제 공식적으로는 이 강의가 국제어 강의이기 때문에 제가 이 온라인 강의를 하는 처음 5주간의 그 온라인 강의 내용은 전부 다 영어로 진행이 될 것입니다. 사실 영어 강의가 한때 굉장히 중요한 그 대학의 요소 중에 하나였다가, 영어 강의가 어느 순간 좀 덜 중요한 것처럼 생각이 됐다가, 다시 최근에는 좀 영어 강의의 비중이 높아지고 있죠. 그래서 이제 학생들이 아마 또 영어 강의에 대한 부담을 좀 최근에는 많이 느끼는 이제 그런 상황이 됐고, 저희 교수들도 사실 영어 강의를 또 더 최근에 와서는 다시 이제 많이 해야 되는 뭐 이제 그런 상황이 됐습니다. 여하튼 온라인 강의는 제가 영어로 하게 될 것이고, 여러분들이 과제 레포트도 아마 실험 결과 보고서도 영어로 제출을 하셔야 될 겁니다. 사실은 예전에는 이 실험 과목들을 학생들이 직접 이 각각 실험에 대한 이론과 실험 방법을 준비를 해서 세미나를 하고, 또 학생들이 예비 레포트도 쓰고, 각 실험 들어가기 전에 이론에 대해서 예비 레포트도 쓰고, 그 다음에 결과 레포트도 쓰고, 굉장히 할 일이 많았었고, 그 다음에 또 기말고사도 봤었고, 그랬는데, 최근에 좀 많이 간소화가 돼서, 이제 이 각 실험에 대해서 설명은 이제 여러분들이 세미나를 직접 준비해서 하시는 대신에 제가 이제 강의를 해드리고, 여러분들이 강의를 시청을 해서 실험을 하시고, 예비 레포트, 사실은 제가 다 이론에 대해서 설명을 강의를 하기 때문에 굳이 예비 레포트를 쓰시지 않으셔도 되고, 결과 레포트만 쓰시는 방향으로 이렇게 좀 간소화가 되고 있습니다. 저희가 아마 기말고사도 보지 않고 여러분들의 레포트를 가지고 평가를 주로 하게 될 것 같습니다. 자, 그래서 이제 오늘은 이 첫 번째 실험에 대한 소개를 해야 되는데, 첫 번째 실험 보시는 바와 같이 이제 heat capacity of gases, 연료량 측정에 대한 실험이 되겠습니다. 지금부터는 이제 말씀드린 바와 같이 제가 영어로 여러분들께 강의를 해야 되겠죠. Okay, I would like to switch to English from now on, and I would like to introduce the first experiment of the Physical Chemistry Laboratory 2, which is entitled Heat Capacity of Gases. As I already mentioned in Korean shortly, for the first 5 weeks, you have to attend the online classes. So every week, I will upload one online class movie, and in each movie I will explain a theoretical background and experimental procedures and result for each experiment. So for the first 5 weeks, then you have to complete watching all these movies I'm uploading. And then later on, you come to the laboratory and perform experiment. Okay, so today I would like to explain the first experiment, which is entitled heat capacity of gases. So here we measure basically things and we get some data. And by evaluating this data, we can get then the final value of the heat capacity of air. Okay. So let me start with heat capacity of gases. So content, purpose, theory, apparatus and reagent, procedure, result, cautions, references. So let me start with purpose of the experiment. So purpose of the experiment. Here we measure heat capacity of the air. And we know that air basically consists of mostly N2 and O2. And both are diatomic molecules. They have common in molecular structure. Okay, so we measure heat capacity of the air. So basically N2 plus O2 and probably some minority gases, but mostly N2 and O2. We measure two different types of capacity, heat capacities. Number one, constant volume heat capacity given as CV. And number two, constant pressure heat capacity, CP. Okay. So you have a system, volume is fixed. Okay. You supply some heat and you would like to increase the temperature. Okay. Temperature by 1 Kelvin or 1 Celsius degree. Okay. So basically heat capacity in this case is how much heat is needed to increase the temperature of the system by 1 Kelvin without changing the volume. Okay, that is constant volume heat capacity. On the other hand, you have a system again, you have external pressure and you have internal pressure. So you could assume that internal pressure and external pressure would be the same in equilibrium. Okay, and that pressure is constant. That pressure doesn't change. Okay, and now if you add some heat, temperature change is 1 Kelvin, for example, how much heat is needed here, and that is constant pressure capacity. In this case, of course, what is going on is that when temperature increases, then of course the volume will increase as well. Okay, according to the ideal gas equation. Okay, when heat is added, pressure is constant, then volume can increase, right? when temperature is increased. And under this circumstance, how much heat is needed to increase the temperature of 1 Kelvin is actually the definition of constant pressure heat capacity. Okay, so we are going to measure both in this experiment. So learn here in this experiment how the ideal gas law. So we learn about ideal gas law already in general chemistry, which is known to be PV equals nRT. Everybody probably knows about it from general chemistry 1. Gas constant R, okay, and first law of thermodynamics. I mean, that is probably a very important thing that you have to learn in this experiment. Now explain the relationship of molar heat capacity and degree of freedom. That is also very important. And as a matter of fact, we have air mostly consisting of N2 and O2. So both are diatomic molecules with a linear structure. So for a given temperature, degree of freedom of N2 and O2 can be regarded to be almost the same. So that is making all the explanation about relationship of the molar heat capacity and degree of freedom rather simple here. Because when molecular structure changes, then degree of freedom can change. Okay, we go to theory now. Work, heat and energy. I think probably we may have all learned about this in general chemistry, but still, let's go through again work, heat and energy. So work is equal to the magnitude of the applied force times the displacement of an object. So work is generally known to be F multiplied by D, F being applied force, D being displacement of an object, okay? But in thermodynamics, it is very important to know that the amount of work is the same as pressure multiplied by the volume change. This is the same as applied force multiplied by the displacement of an object. So if you think about a cylinder, so you have this kind of piston, okay, and now inside the cylinder you have air, okay, you have external pressure, okay, external pressure exerted to the system, you have air here, right? Now in this cylinder, consider the two-dimensional cross-section. You have an area A, okay. Then when you consider the vertical distance of the system, and that should become D, right? So when you think about a situation that for some reason volume is changed, so volume is changed. Initially volume is like this, volume of the system is like this, but after a while volume increased like this, and now we consider the change of the vertical distance of the cylinder to be now D here, okay? And now then, how much volume changes? How much volume changes here? That is A multiplied by D, right? So you have a cylinder and you have a piston which is vertically changing, okay? And then the volume increases for some reason, probably temperature increases, volume increases, and the volume increase is basically the same as the area multiplied by the vertical distance change, okay? Now, the pressure, this is external pressure, which is actually then applied to the system. This pressure is basically force for a given area, right? So by definition, pressure is given to force divided area. So when you multiply this, P Ex multiplied by delta V, and then it becomes like A multiplied by D multiplied by F divided by A. So A in the numerator and denominator, they cancel out with each other. So what is only remaining is dF, which is basically the same as FD, and that is basically work, the amount of work. Okay. So I think this is what we learned from General Chemistry 1, but I try to remind you of what you already learned in General Chemistry 1. Heat. Heat is energy that spontaneously passes between a system and its surroundings in some way other than through work or the transfer of matter. So in thermodynamics, generally we only consider the volume change associated work. So there could be some other works like electrical work, but in general chemistry, in thermodynamics, at the very basic thermodynamics, we ignore all the other works and we only consider the work associated with volume change. So the internal energy of the system can change either the work associated with the volume change or heat. Okay. So the heat and work, these are two different paths that can change energy of the system or energy flow between system and surrounding. Okay. So energy is defined as the capacity of a physical system to perform work. Okay. So then we go to internal energy. This is very important, which is related to the first law of thermodynamics. Okay. So internal energy, U, generally given as U in thermodynamics. So internal energy is total energy of the system, including the kinetic energy and potential energy as a whole. Okay. So kinetic energy, potential energy, all included for a given system. That is internal energy. I think probably you're going to learn more in detail about internal energy in physical chemistry too. Okay. Internal energy is a state function of a system. So, I mean, in thermodynamics, we have two different types of functions, state function and path function. State function and path function. And state function has a property whose value does not depend on the path taken to reach that specific value. So temperature, pressure, volume, internal energy, enthalpy. So you start from a certain value, you end up with a certain value, then you have delta something. For example, let's say that internal energy, you have initially internal energy over here, and finally you have internal energy over here, then delta U value. That doesn't change depending on the path, how you how you arrived actually to the final value from the initial value. Only the initial value and final value matters. And you can say, okay, delta U. And that is the nature of state function. On the other hand, path function has properties. Path functions have properties or quantities whose values depend on the transition of a system from the initial state to final state. So, for example, heat and work, they are path functions. I don't want to go into that much details of state and path functions today in this lecture, but I think in physical chemistry 2, we are going to learn about very in detail why heat and work are path functions, while most of other thermodynamic functions like enthalpy, well, internal energy, entropy, Gibbs free energy, they are all state functions. And also temperature, pressure, volume, they are all state functions. Okay. Okay, first law of thermodynamics. The first law of thermodynamics is a version of the law of conservation of energy. So conservation of energy, that is very important phrase. The law of conservation of energy is first law of thermodynamics. The second law and the third law of the thermodynamics, they are all related to entropy. The first law of thermodynamics is related to the internal energy and conservation of energy. So now, according to the first law of thermodynamics, internal energy, the internal energy of an isolated system is constant. I have to introduce system surrounding and the whole universe, okay? So the part of the universe that you are interested in, your reactor, for example, okay, or your system in which the gas molecules are confined. This is the system, and the rest surrounding. And system and surrounding all together, we call this universe, okay? This universe is, in thermodynamics, in this universe is defined to be an isolated system, okay? An isolated system. This universe is isolated system. And what does it mean with isolated system? In isolated system, matter and energy, they cannot be exchanged with outside, okay? If you define an isolated system, matter, energy, everything is actually confined within that isolated system. And universe, the whole universe is defined as an isolated system in thermodynamics. So the total internal energy here of the universe should be constant, okay? And this is conservation of energy. Of course, the system and surrounding, they can exchange energy, right? They can exchange energy. Whether they can also exchange matter or not is depending on what is the nature of your system, whether it is an open system or closed system. But anyhow, the surrounding and system, they can exchange energy, but the whole universe is an isolated system, so that the energy, the internal energy of the whole universe is preserved. And that is conservation of energy, okay? So energy cannot be created or destroyed. They can be only exchanged between system and surrounding. The energy can go from here to there to here. But when you consider the whole universe, the total amount of energy, that is always the same. And that is what first law of thermodynamics says, okay? So internal energy is the amount of heat supplied to the system minus the amount of work derived from the system. So I'm going to explain about this sentence more in detail in the next page. So this is about how the system can then exchange energy with the surrounding. As I said, the whole universe is an isolated system. So the whole universe, within the whole universe, the total amount of energy is always constant. But inside the universe, you have system and surrounding. They can exchange energy. Okay. Now, how can they exchange energy? In basic thermodynamics, we consider heat and work, two different paths, which is available for exchanging the energy between system and surrounding. Okay. Okay, so this is your equation. So delta U, internal energy for state function. So for state function, you can use this delta, right? The capital delta for the amount of change, okay, from the initial state to the final state. So now Q is the amount of heat added to the system, W work done on the system. So it is actually important to know that W is minus P delta V. So when there is a constant external pressure, when volume of the system increases, okay, and that is actually the situation, the system is doing work. When system does work, then internal energy decreases. So we have to put this minus sign, right? When system's volume decreases, that means that the surrounding is doing work on the system, okay? And when volume decreases, then actually work is done on the system. So work is done on the system, then system's volume decreases, okay? In this case, work is positive, okay? Because then internal energy of the system increases. When work is done by the system, then volume increases, okay? In this case, work is negative because work is then decreasing the internal energy of the system. Well, when heat is added to the system, Q is positive. When heat given off by the system, Q is negative. That is rather simple to understand. Okay, ideal gas. Ideal gas. I think we can go rather fast with this because we already learned about the nature of ideal gas in General Chemistry 1. Gases are made up of very tiny molecules, no molecular volume. Okay, gas molecules demonstrate rapid motion in straight lines and in random direction. Gas molecules have no mutual interaction. Gas molecules undergo elastic collision. Okay, I mean the gas molecules, they can make collision. Okay, they can make collision, but and then probably after collision, they can change the directions of movement. Okay, so either gas doesn't mean that they do not collide with each other, but they can collide with each other during the random motions of each molecule. Okay, and when they collide and then they change direction of the movement, there is no loss of kinetic energy. That is what is meant by the elastic collision, the terminology elastic collision. I mean, on the other hand, inelastic collision means that, for example, they collide with each other and then kinetic energy is lost, so they become slower. Or probably one molecule becomes faster and the other one slower. When there is change of kinetic energy or loss of kinetic energy, so that they become slower. Okay, this is inelastic collision. So this is actually what we see more in nature, right? If two cars collide, okay, then they stop. This is a more inelastic collision, I would say. Okay, and the energy is actually dissipated more to the surrounding by the other paths. But the gas molecules in ideal gas, they are assumed to make only elastic collision. After collision, before collision, and after collision, the kinetic energies remain the same. There is no loss of kinetic energy. The average kinetic energy of gas molecules is proportional to the Kelvin temperature. I think this is also related to the equipartition theorem, which I will explain later more in detail. So when you think about a one-dimensional kinetic energy, for example, so this is when you think about a one-dimensional system, you have only x-axis. Okay, so molecule can only move right and left, right and left. So the kinetic energy is half mvx square. So vx meaning the velocity along the x-axis. Okay, now this can be regarded as half kt, half kt. So k meaning the Boltzmann constant. Okay, k Boltzmann constant. I think you will learn more in detail in physical chemistry too. Okay, so this is Boltzmann constant. So half kt, T of course temperature. So and then when you think about two-dimensional molecular kinetic energy, so and then for two dimension, so this is one-dimensional system. Okay, for two dimension, a molecule can move along x-axis and y-axis. Then kinetic energy is then, well, kt, right? So half kt plus half kt. So for each dimension, the kinetic energy is half kt. So for two dimension, kinetic energy is kt because half kt plus half kt. In three dimension, then kinetic energy becomes then three half kt. So this is also associated with the degree of freedom that I explained at the very beginning of this class in the propose. So we would like to also understand about the relationship between the degree of freedom, okay, and the energy, the capacity. So each dimension, the kinetic energy of each dimension corresponds to one degree of freedom, and according to the equipartition theorem in statistical thermodynamics, each degree of freedom corresponds to half kt as far as the kinetic energy and rotational energy is translational energy and rotational energy is concerned. We are concerned. Okay, so probably I will talk about that more in detail later. I'm going to explain about this degree of freedom issue later more in detail. Okay. So ideal gas law Well, Boyle's law, pressure and volume inversely proportional to each other. Charles' law, temperature, volume proportional to each other. Avogadro's law, number of moles of molecules and volume proportional to each other. All together, you come up to the conclusion PV equals nRT, ideal gas equation, right? I think everybody knows about that. Okay, now we go to heat capacity. Actually, the important part of our experiment, okay? So far, what I explained you for the first 9 pages or 8 pages at the beginning, I mean, if you have difficulty to understand any part of the class that I gave you so far, then probably you can go to chapter 5 of the General Chemistry 1, okay? Chapter 5 and Chapter 6 of the General Chemistry 1 of the textbook that we use for General Chemistry 1 in our university, okay? Chapter 5 is about ideal gas equation. Chapter 6, more about energy, heat walk, this issue. Okay, now we move to heat capacity. Energy required in raising a substance's temperature 1 Kelvin up, right? 1 Kelvin up at a given pressure Cp or at a given volume constant, volume heat capacity, Cv, okay? So molar heat capacity, the molar heat capacity is the heat capacity per mole, of course, of pure substance. So heat capacity is given as C, the molar heat capacity given as C bar, right? The molar heat capacity, C bar, okay, of a substance results from the amount of absorbed heat dQ and the temperature change dT per mole, right? Well, in general chemistry, probably we learned that the heat capacity to be like this. For the infinitesimal change of the temperature and heat, then we can actually define the heat capacity to be dQ over dt. Okay. But I don't want to go into that details about the state function and path function. But in the case of state function and path function both, when we consider infinitesimal change, very very small change, then we can for both we can use this d notation, right? This derivative notation for the infinitesimal change, a very small change, okay? But when you make integral, okay, when you make integral of this, okay, when you make integral of this, then this dt integral becomes then delta t. T is one of the state functions, while in the case of path function, okay, q is one of the path functions, it becomes just simply q, right? For path function, you cannot use capital delta, this Greek symbol delta, because this delta, Greek symbol delta, can be only used for the state function. Basically, delta t is tf minus ti, okay? So delta t is not dependent of how temperature changes from ti to tf, right? So initial temperature and final temperature, only both values matter. And the way how the temperature changed from ti to tf does not matter for delta t. So one cannot say in this case t is a state function and we can use the capital Greek delta for describing the change of the value. But in the case of q, it is a path function. So for heat and work, it actually matters how the change is made, which path it went through. So in this case, integral becomes then simply q. So probably I think everything is actually more the subject of physical chemistry 2 class, okay? But I want to make sure that because sometimes for some symbol I use capital, I use the Greek symbol delta, sometimes d, and sometimes I don't use any of them, so why? And that is related to the issue of state function and path function, okay? Anyhow, so for the infinitesimal change of the q and t, the heat capacity can be defined to be like this. And when we divide it by the number of moles, of course, n number of moles, okay, number of moles, then we have then molar heat capacity, okay, and then this can be then rearranged to become like this, okay. And now we already learned from one of the previous slides that delta U internal energy change is Q plus W. So W is minus P delta V, as I already mentioned. Okay, and now we learned that when you make integral here like this, and that becomes Q, and that I think probably in this case, for me, I would better write like this. Okay, and so probably then I think it's better to write like this. Okay, so I think probably this Greek delta is more correct. Anyhow, I mean, probably D is not completely incorrect, but I think, I mean, delta is probably a better, because here volume change is also given as delta. So I think it's better to give like, so, okay. Relationship of molar heat capacity and degree of freedom. Can we go with the degree of freedom issue? I already told you that I'm going to explain about degree of freedom later more in detail. And now here we go with the issue degree of freedom. So molar heat capacity under two different conditions. So delta U, when volume is constant, so delta U is Q plus W, and that is Q minus P delta V, okay? When volume is constant, then that disappears, okay? And delta U becomes the same as Q. And as I already mentioned here in the previous slide, when you remove this, okay, and delta U is simply NC bar delta T, right? So NC bar delta T. Now I like this more with the Greek symbol delta. Okay, so and then this can be rearranged to be like this. Okay, now from this here, from delta U being NCV molar constant volume capacity, delta T minus P delta V. In the first condition, isochoric condition, volume is constant, so we removed actually this. But in the second condition, isobaric condition, where pressure is constant, but volume does not need to be constant, then we have to then consider both, right? So it is given here, and then it can be rearranged to be like this, okay? That is simple rearrangement. It's not that difficult to understand how it moves actually from this equation to this equation. So I would like to go rather fast when a problem is just a matter of just simple mathematical rearrangement, nothing else than just a rearrangement, okay? All right, so relationship of molar heat capacity and degree of freedom. Molar heat capacity under two different conditions, okay? So that is the molar heat capacity. And now when you consider that, I mean, dq is du minus dw, then we can change actually this to this equation, okay? So minus dw, when volume change is zero on the isochoric condition, then minus dw is zero, okay? On the isobaric condition, of course, then dp is zero, but dv is not zero. The p dv is actually corresponding to some value, okay? Regarding heat capacity, so for isochoric condition where volume change is zero, then we can say that the heat capacity constant volume molar heat capacity can be given as this term, while in the case of Cp bar, the molar heat capacity under constant pressure can be given as this equation. This is basically a summary of what we have already learned in the previous slide. We already learned here that CV bar is this and CP bar is this. And in the next page, only the Greek delta value is displaced by the D. In the previous slide here, we considered substantial change of the state functions, while in the next slide, we only consider infinitesimal change of that state functions, those state functions, okay? So basically, but describing physically the same meaning things. Okay, now then we start with this equation here. We start with this equation. Now, when you consider this under isobaric condition, PV equals nRT and PdV equals nRdT, right? For a closed system, number of moles remaining constant and pressure is constant, then volume change can be only associated with the temperature change. Okay, so under isobaric condition that pressure is constant, then we can actually apply this equation. Then this part of the equation changes to be like this, okay? And then ultimately we come up to this conclusion that CP minus CV is actually NR, or the molar CP minus molar CV becomes R. So you are going to measure constant pressure heat capacity and constant volume heat capacity, both in this experiment, okay? So, and then probably you are going to be able to verify by yourself whether your CP and CV values are meaningful by considering this equation. You get your CP bar and CV bar values, okay? And then you make a subtraction of CP bar minus CV bar. And then if the resulting value is close to gas constant R, then most likely one can say you did your experiment quite good. But otherwise, if your deviation of your data and the R value is too much, then probably something went wrong. Then you have to, of course, think about why the experiment did not proceed well. Okay. Now here we go, the degree of freedom issue. As I already mentioned, in equipartition theorem, I already mentioned about equipartition theorem previously. So according to equipartition theorem, we are going to learn about this also in detail in statistical thermodynamics, which is a scope of physical chemistry too, okay? And you're going to learn about equipartition theorem there more in detail. Let me introduce equipartition theorem shortly. Equipartition theorem says that in a sample at a temperature T, all quadratic terms, these are all quadratic terms, okay? The contribution of each quadratic term is half kT, okay? So for a molecule, generally, when you have n atoms, probably for this lecture, this is physical chemistry laboratory lecture, not the completely pure theoretical lecture. So I do not want to devote much time for explaining that fundamental theoretical aspect. Let me go rather shortly. If you have n atoms in a molecules, then basically you have 3 degrees of freedom. And you have basically, if you have n atoms in a molecule, then you have 3n degrees of freedom, okay? So because when n atoms are all separated, each atom can move along x, y, z axis. So each atom can have 3 degrees of freedom because we are living in a 3-dimensional space and each atom can move along x, y, z axis, okay? So each atom 3 degrees of freedom. So when n atoms are combined to form a molecule, still there's a 3n degree of freedom should be preserved. That is the conservation of degree of freedom. Okay. So Now, but when n atoms, they form a molecule, they cannot move freely apart from each other, so they have to move somehow together. So this degree of freedom should be rearranged. So out of 3n, 3 goes to translation. 3 goes to translation. That means that the whole molecule moves along x-axis, y-axis, z-axis. Okay, 3 degree of freedom. Now, for non-linear molecule, there are 3 degree of freedoms for rotation, but in this case, we are considering a linear molecule now. You have N2 and O2. They are both linear molecules, right? Because N2, O2, I mean, a diatomic molecule can be only linear, right? Linear molecule. For linear molecule, this can be effective rotational axis, okay? So this can be also effective rotational axis. So 2 rotational degree of freedom, half I omega x square, half I omega y square, okay? These are rotation like this or like this, okay? So my rotation axis like this, and it is rotating like that, okay? My rotational axis is like this, it is rotating like that, okay? There are 2 different degrees of freedom. So, and then you may wonder why not this rotational degree of freedom. So this rotation for a linear molecule corresponds to this kind of rotation, as if the pencil is just rolling on the table, okay? And this is not effective rotation, because in this case, the center of mass and your mass actually are on the same position, okay? So the momentum of inertia is 0. So there is no effective rotational energy if rotation is given like this, okay? So for linear molecule, there is only 2 different, for linear molecule, there are only 2 rotational degree of freedom. Okay, and then now among 3n, 3 goes to translation, 2 goes to rotation, and the rest, 3n minus 5, it goes to molecular vibration. It goes to molecular vibration, okay. 3n minus 5, it goes to molecular vibration, okay. Now, we are at room temperature. Generally, we are doing the experiment at room temperature. At room temperature, we only consider this translation and rotation. So we can then we can just ignore vibration. So the molecular vibration in the case of N2 and O2, they vibrate this like this. Okay, this is the symmetric stretching vibration. But at room temperature, we ignore this vibration. Okay, because this vibrational excitation takes place actually at much higher temperature. So regarding the vibrational motion at room temperature, the vibration of the molecule is not fully not considerably excited. So we only consider that the translational motion and rotational motions are fully excited at room temperature. So we regarding degree of freedom of molecule at room temperature, we only consider translation and rotation, because there are 3 degrees of freedom for translation and 2 rotational degree of freedom. We can then give the total kinetic part of the energy like this, the translational kinetic energy and rotational kinetic energy. So each quadratic term, there are 5 different quadratic terms. So there should be 5 half kT of the total energy for this system, total energy of this system, okay? Yeah, so each quadratic term corresponds to half kinetic kT. So we have 1, 2, 3, 4, 5. So it becomes then 5 half kT, because we consider 3 quadratic terms, each term corresponding to each kinetic energy of each direction, and also 2 rotational quadratic terms corresponding to this rotation and this rotation. Okay. So that means that according to equipartition theorem, U should become then 5 half, well, KT, and this 5 half KT, so this half KT, that can be attributed to a kinetic energy or an energy of a molecule, right? This half kT corresponds to the energy of a quadratic term for a molecule, right? For a molecule. And now within a system, so as far as internal energy is concerned, then you have to multiply number of molecules, okay? So here, capital N being number of molecules, okay? And of course, that can be then rewritten as 5 half KT number of moles and Avogadro's number, okay? Right? And then one can say when K and Avogadro's number are multiplied, it becomes then gas constant, okay? So ultimately then you can say, okay, this becomes then 5 half RT multiplied by N, number of moles. So as far as when you consider the energy for 1 mole, of course, if your energy is actually defined to be the energy for 1 mole, then you can of course remove that as well. Okay, so if you consider energy of 1 mole of the system, then you can actually then omit this number of moles, small n as well. So it becomes then 5 half RT. So now it is given as FRT like this, but now we learned that in our air sample consisting of diatomic molecules N2 and O2 and at room temperature, the degree of freedom is 5. 3 of them translational motion, 2 of them rotation. Okay, so degree of freedom 5. So ultimately it becomes then 5 half RT. Okay, according to definition, we have to multiply the number of quadratic contribution degree of freedom. So I mean, in the previous slide, we already considered that the degree of freedom here we can consider is 5. Vibration neglected. For diatomic molecules, only 2 degrees of freedom for rotation and 3 translation. So in total 5. Okay. So here we go. Degree of freedom, an independent parameter that is necessary to characterize the state of physical system gases, considering 3 kinds of motions, as I already mentioned, translation, rotation, vibration. So, but vibration can be neglected, okay? So in standard temperature, vibrational degree of freedom is not considered, it's neglected, because for the excitation of vibrational motion, much higher temperature is needed than room temperature for standard temperature. So the air is composed of mainly diatomic molecules O2 and N2. So this is very important because air mostly composed of diatomic molecules, we can consider only 2 rotational degree of freedom, right? So that is actually the reason why I emphasize actually from the beginning that it is important that air can be regarded as basically a substance consisting of diatomic molecules, because for diatomic molecules, you have only for diatomic molecule, the only structure you can imagine is a linear structure, and of course O2 and N2 both are a linear both are linear molecules, and for them you have only 2 a rotational degree of freedom. For translation, you have 3 degrees of freedom. So I think I already explained about them, and just the same content is repeating. So there would be 3 translational motion, x, y, z, and 2 rotational motion, x, y. So there are 5 degrees of freedom, 5 half RT. Okay. Now this is very interesting here. So you have to look at this. Molar heat capacity is given to be like this. Okay. So on the constant volume, the heat capacity, molar heat capacity given as the first order derivative of the internal energy with respect to temperature divided by the number of moles, right? So CV, that is basically du over dt, right? I think we have already learned about this, right? Let me go back. Yeah, I think we have already learned about this. Yeah. Yeah, we have already learned about this, right? The same one. The same one is given here, right? And then, well, du, you, we learned that for air, we learned that T, so du should become then 5 half R then dt, right? Which is given here. And all together at the end, your CV, molar constant volume capacity becomes then 5 half R, right? So your CV bar should become then 5 half R. And then previously we learned that CP minus CV, that should become R. That is also what we learned in the previous slide. I'm not going to go back, but you will find in one of the previous slides that this is this relationship between CP bar and CV bar. So CV bar is actually 5 half R, and you have this relationship. So then CP bar is then 7 half R, right? So now in this experiment, we measure CV bar and CP bar, and your analysis, well, ideally, in principle, should result in the CV bar value of 5 half R and CP bar value of 7 half R. Okay. Whether your experiment shows these values or not, I don't know. I mean, if your experimental values are close to these values, then you are very, I mean, you are quite good or quite lucky. If your values are too far away from 5 half R for CP bar and 7 half R for CP bar, that is also a case. Then we can discuss why your values become so different from the theoretical values. You can think about it, and you can also speculate. What would be the reason for that deviation from the theory and your experiment? Okay, I already mentioned about this, so CP bar 5 half R, okay, and then CP bar 7 half R, okay. So in principle, at room temperature for diatomic molecule, CP bar should be this value, CP bar should be this value. These are the theoretical values at room temperature, CP bar and CP bar, where degree of freedom for oxygen, nitrogen, all assumed to be 5, okay. And vibrational degree of freedom then neglected. Okay, then we are going to now learn about, well, isobaric condition. Okay, let me go to enthalpy. And now here we go. Okay, probably. Okay, let me go fast about enthalpy. We also learn about enthalpy in general chemistry. Okay. On the isobaric condition, when pressure is constant, okay, enthalpy given as H in thermodynamics, enthalpy is defined as U plus PV. So that is definition of enthalpy. enthalpy, right? So that is definition of enthalpy. Enthalpy is given as H, and its definition is U plus PV. Enthalpy is, of course, U, internal energy, P, pressure, V, volume, right? Enthalpy is the amount of heat content used or released in a system at constant pressure. So the heat on the constant volume was change of the internal energy. Enthalpy change is the heat on the constant pressure. So isochoric, right? When V is constant, Q is basically then delta U, right? So when P is constant, Q is delta H. That is actually what is given here in this slide. I think this is also what you learned already in general chemistry. So why is it like that? So you start from the definition of enthalpy, which is given as U plus PV, okay? When you consider dH, okay, H plus dH, then H plus dH can be given as U plus du plus P plus dP plus V plus dV, okay? Then you apply first law of thermodynamics, du equals dq plus dw, and dw is minus pdw, okay? And when you apply all of them together, and then at the end problem, you can do it by yourself. So when you actually rearrange this part, then U plus du plus pv plus pdv plus dpv plus dpdv, okay? And that is, for example, given as H plus dH, okay? Then H, U plus PV, you neglect it, then dH becomes then du pdv, dpv, and then dpdv, and du is now given as dq minus pdv, okay? Then pdv minus pdv, they cancel with each other, okay? And then, of course, that should be zero when pressure is constant, and we neglect this because this is too small, so we neglect it. Then ultimately we come up to the conclusion that dH becomes the same as dQ, right? So then Cp is simply dH over dt, so first the derivative of the enthalpy with respect to the temperature. So that is another physical meaning of the constant pressure heat capacity. So, and then you can rearrange this like this. Okay, from now on, this is more related to the real experimental procedure. What is given here is the following thing. Let me probably show you the experimental setup first and then come back. So there are a lot of equations, but I mean, they are not that difficult from now on. This is your experimental setup. Let me explain this first and then go back to these whole equations related to this picture, experimental setup. Now, when you look at this part more carefully, what you can see is that you have two electrodes and then there is a heating wire. Okay, so you apply some voltage here. You apply some voltage, okay, and you apply voltage, and then electrical current goes in. So electrical current is flowing, and this voltage and current energy, this electrical energy is converted to heat here. And this is the same as the traditional tungsten lamp. So you supply the electrical energy, then you have a tungsten wire, which is then glowing, which is heating. So this is the principle of the tungsten, the old tungsten lamp. Nowadays, probably not that many people use it. But anyhow, so then this electrical energy is converted into heat. So in this way, heat is supplied. When heat is supplied, so then you can actually forget about this. In real experiment, we are not going to use this. So you can actually forget about this part. So you just close it. And then what is going to happen is that when you heat the wire, so that when you heat the wire by supplying the electrical current, so that heat is supplied to the system, this is basically your system where air is filled, okay, and then this piston will go down because volume increases. Volume of the system increases. So basically, electrical current is supplied, electrical energy is converted into heat here. So it is heating the air, and then the volume will actually increase because heat is provided. The volume will increase and doing work, okay? And how much volume changes can be measured here. Okay, so here the summary is given. Electricity converted to heat here in this part, where the heating wire is actually connected between two different electrodes. So electricity converted to heat, energy in metal wire should exist somewhere here. And heat energy is given, that heat energy, electrical energy converted to heat energy given to air, and then air is doing work, volume expansion takes place, and that is measured here by the downward shift of the cylinder, okay? And you have here the values that you can read for the volume change, okay? All right, when you understand this, then the whole equations are rather simple to understand. So it looks complicated, but it is actually not that complicated when you look one by one. So first, measuring heat capacity at isobaric condition. So pressure is constant, isobaric condition, okay? Pressure is constant, isobaric condition. Volume is constant, isochoric condition, as we already learned in one of the previous slide. Electrical energy converted to heat. So when electrical energy is applied, this is the voltage which is applied to the heating wire. So voltage we measure actually from the controller outside. I is the current which flows through the heat wire. So basically in the previous slide I gave V voltage, but here we use E. So and then voltage, okay, multiplied by current, multiplied by the time period during which the electricity is applied, that becomes the total amount of energy, and that energy is assumed to be fully converted to the heat. So this is then Q. Now here we are using actually delta, because now we can consider Q as a kind of state function under this circumstance. Okay, Q is in principle not a state function, but now when you consider that this electricity is the only path to provide heat, then this heat can be regarded as a state function. So here delta Q is given. So the electrical energy is converted to the heat energy, right? When you measure this, and then when you control this time for which the electricity is applied for a given voltage and current, then you can measure how much heat is provided. So when you provide electricity for longer time, more heat is provided. Shorter time, less heat is provided. Okay. Okay, isobaric condition, continuing. At constant pressure, isobaric condition, the temperature increase delta T induces a volume increase delta V. So heat is provided, temperature increases, and then volume increases. Basically, we measure the volume increase, right? So according to the ideal gas equation, PV equals nRT. When pressure is constant, then we can use the relationship between volume change and temperature change like this, okay? And then we can then rewrite the equation like this, okay? And then this equation becomes the follows. Cp, when you start from this, okay, when you start from this, let's say, for example, C bar equals 1 over n, and then now you consider delta T and delta Q, okay? And then delta Q here in our experiment is EI delta T, right? And then EI delta T, okay? And then delta T is same as delta V over T, okay? All together, this and the delta Q in the previous slide, all together, this becomes like that, okay? So you have to then combine this, and this all together, right? And it becomes like this, okay? So now here we have an equation from which we can develop more for use of the evaluation of our experimental data, okay? So remember this equation. On the isobaric condition, we can also think about this kind of equation. So PV equals nRT. So T PV, that is constant. For standard condition, T0, P0, PV0. For non-standard condition, for 1 mole, okay, T P molar volume, okay, standard condition, that means that for 1 mole, standard pressure, standard temperature, this, and non-standard temperature and pressure, this, they should be the same because this is constant, right? So, and then we can go, this can be rearranged to this equation. And then, of course, I mean, V is the same as Vm multiplied by number of moles. This is molar volume for 1 mole, okay? And then this is number of mole, and this is volume, okay? So here V0 is standard condition 1 mole volume, standard pressure P0, standard temperature. This is non-standard any temperature, non-standard any pressure, okay? And then we can come up to this equation, and then we combine this and this, okay? We combine this and this. Here, of course, I mean, you have to consider that V over N becomes then Vm here, V over N, that should become Vm, okay? When you combine this and this together, and then you can come up to this equation, okay? So now we have an equation which we can use actually for our experiment, okay? So this is very important equation. Now, what we are doing is actually the following thing. In the experimental setup I showed you, you provide heat during different time intervals, okay? And during the different time intervals, proportional to the time interval, heat will increase. That means that you provide electricity with a given E and I value for a certain time, okay? And then heat will be provided, you measure delta V. You cool down the system, come back to the original setup, and then you use delta T with a longer time or shorter time. You use actually delta T with different values, and then you measure delta V at each delta T, okay? And then you can determine delta T over delta V, okay? And then this EI, these are the voltages and current which you use, and they should be constant. Well, pressure is actually the pressure of your experiment, which should be the same during your experiment, okay? Standard pressure, standard volume, standard temperature, and then you can determine Cp bar. Experimentally, what you are actually measuring is actually delta V as a function of delta T, so that you have to experimentally determine this one, okay? And then Cp bar can be determined. Now, the only thing which is left is how to determine this p-value. I mean, E and I, these are the values that are from, these are the values from the controller, the electrical controller, right? Which is connected to two different electrodes which provide the electricity to the heating wires. P is calculated from the atmospheric pressure minus the pressure reduction due to the weight of the syringe's plunger. So this syringe's plunger, what does it mean here? This part. So you have atmospheric pressure, but this syringe's plunger exert the pressure downward. So that subtraction of the pressure inside the system due to the downward force of the plunger should be considered to determine the actual pressure of the system. So pK, this is the amount of pressure you have to consider for reduction due to the weight of the syringe's plunger, okay? And that is the mass of the plunger. That is the mass of the plunger. And G, acceleration constant, okay? Acceleration of the gravity, of course. And F, here, F is the area of the plunger. Area of the plunger. And then this F is not force here, but F is area. F is this area, okay? And this area, plunger's cross-sectional area, and the mass multiplied by gravitational constant, okay, exerted downward. That is the pressure, okay. So as I already mentioned, this is force divided by area. That is the pressure. So this is area. F is area of the plunger. So this is the pressure exerted downward by the plunger's weight. This should be subtracted from the atmospheric pressure to determine the correct pressure inside the system. So atmospheric pressure is measured. Then you consider this, the reduction of the pressure due to the weight of the syringe's plunger, and then you can calculate. So of course, I mean, this is something in principle you have to measure correctly during you do your experiment in your lab, right? And this is the value you can take and then subtract from your measured atmospheric pressure in your laboratory. Okay, I'm going to skip this because I already explained about this. Now here we go. It's a little bit complex. Now, so far I explained about how to measure this Cp bar, right? How to measure Cp bar is explained. Now I go to Cv bar, right? This slide looks actually quite complicated, but when you look actually one by one, there is actually nothing special. This is actually one of the equations we have already seen in one of the previous slide, I think. Cv bar equals then, because let me see whether Q minus P delta V. Cv bar should be Cv bar. Yeah, I think that probably you have to combine this, okay, and then also this. You have to combine this too, And then you can come up to that equation. I think because on the constant volume, the U becomes same as dq. So on the constant volume, this is replaced by dq, and then this can be replaced by p dv. Okay, and then this delta is changed to Greek capital delta. Okay, so when this d are all changed to capital delta. Okay, and then the equation should become like this. Okay, should become like this. Okay, and now we start from this equation. Q, delta Q, EI delta T, we have already learned about that. The amount of heat provided should be EI delta T. Okay, so, and then now delta T, how we change delta T? Well, the ideal gas equation, the total differential, it becomes like this. And then when D is replaced by delta, it becomes like this. So delta is replaced by that. So when you change delta Q to EI delta T and delta T to this, equation becomes a little bit more complex. It becomes like this, okay? And now you have to think about delta V. So it is a little bit strange that we have to consider delta V, even if we are considering the isochoric condition where volume is constant, and that is because the manometer is actually the apparatus which measures the pressure. That actually induces some volume change when pressure is changed. So the system itself doesn't make any volume change, but the manometer connected to the system, that actually induces some change when pressure is changed. So that should be considered because that is connected to the system. So that is that can be regarded as a part of system, right? So delta V is the difference of volume in manometer, not the difference of volume in bottle. Because it comes into the difference of volume in manometer, we should consider that. So, and that change of the volume of the manometer induced by the pressure change, that is given alpha. So I'm going to explain about this alpha more in detail in the next slide. So delta V here should be converted into alpha delta P, okay? And then here again, ideal gas equation looks complicated, but when you look at one by one, so I explain here how each term is changed to the next term in each blue box noted. And if you look at them one by one, well, it's simply a rearrangement of the equations. It's nothing special. Anyhow, important thing is that we are coming up to that. We are coming up to this equation. So CV bar is basically described by this equation. What we are measuring experimentally is delta P over delta T. That is actually what we are measuring. All the others, they are all constant. Alpha constant, P, V, well, all others are constant, okay? The actual volume of the system, actual pressure of the system, standard pressure, standard volume, standard temperature, all known. Then what we measure is when we change the interval, we apply electricity to the heating wire. This is delta T. We can change delta T. And for every delta T change of pressure, delta P will be different. In this case, the manometer is connected to the system. So delta P will be changed. And we measure then delta T over delta P. So when we experimentally determine this, then the rest are all constant. So we can determine this one. Okay. Now, regarding alpha is pi r square multiplied by, this is the pi r square is the cross-sectional area of the tube, okay? Probably I can show you the system more in detail, how it looks like. Now, in this case, the system looks like this. You provide heat, EI fixed, delta T is varied, then Q, delta Q is varied as well. So when you provide different amount of heat to the system, now the system's volume is regarded to be the same, but the volume slightly changes because the pressure. So when actually you provide more heat, then this liquid here will move up, corresponding to different pressure values. This is the apparatus which measures the pressure inside. But during the pressure measurement, volume of this part will slightly change. So that should be considered, okay? So when you think about this part here, like this, your liquid is filled, liquid is filled, okay, this tube, and that is actually pi r square, and then that is the movement of the distance, right? So that is the pressure. You have the scale where you can read the pressure, right? And then, yeah, pi r square, the radius of this tube where liquid actually moves like this, the radius is 2 millimeter. The pressure change is actually alteration of 1 centimeter in length. So when pressure changes 0.147 hexapascal, that corresponds to the change of the distance of 1 centimeter. So cube pi r square with radius of 2 millimeter, change of 1 centimeter of the liquid, okay, then volume change is actually pi r square 1 centimeter for the change of the pressure of 0.147 Pascal, hectopascal, right? So that is defined value for a given manometer. So you can change that. You can just use that. So here I'm showing this equation again in this case. So previously, for the isobaric condition, you have to determine delta T, delta V ratio. Here you have to determine delta T, delta P ratio. Okay. And then the rest all constant. So you can determine the CP V value and CP bar value and CV bar value. Okay. Reagent apparatus. I think most important parts are all done. The explanation about most important part about theory and experiment are all done. Okay. So reagent apparatus, nickel electrode, rubber stopper, chrome nickel wire. This is chrome nickel wire. That is the wire where electrical current flows and which glows, which provide heat, right? One-way stopcock, three-way stopcock, Mario flask, precision manometer, which measures the pressure change as a function of the change of heat, the amount of heat, connecting cord, a syringe, a silicon tubing, rubber tubing, and Cobra 3 basing unit. And that is the unit which provide electricity and current to the system. You can see all how they look like. Probably in the laboratory, you are going to see by yourself, and I think you will be able to realize rather fast what is role of each apparatus. Okay, so rubber stopper, Marriott flask, stopcock, precision manometer. So you put actually this here, okay, and then you put two different electrode. They are connected to your heating wire, and then you have some electrical wiring, and then you have this. What is the name of the electrical controller? The Cobra 3 basing unit. So you have Cobra 3 basing units of providing electricity with a given E and I value, and then Q, and depending on the delta T. So when you increase the delta T, then more heat is provided. Then, of course, more delta P or more delta V values will be then recorded. Rubber tubing, Cobra 3 basing unit, syringe. Okay, procedure. CV value. Determine the CV bar value, molar constant volume heat capacity. Insert the two nickel electrodes into two holes in the 3 holes rubber stopper. So that's actually what I mentioned here. So you use actually probably 3 holes rubber stopper, and 2 of them you just put the electrode. You have rubber stopper with 2 holes, then in each hole you put the electrode, okay, and then they are connected to here. Screw 2 pieces of chrome nickel wire. So you have stopper and you put 2 electrodes like this, and then on the other side you connect chrome nickel wire. Chrome nickel wire, 2 pieces, okay, two wires. They are connected to 2 different electrodes, which are long, about 15 centimeter long. Each wire is 15 centimeter long, the 2 of them, into the clamps between these 2 electrodes so that they are electrically connected in parallel. So insert the one-way stop cock into the 3rd hole of the stopper and insert the prepared stopper in the lower opening of the bottle. So you have the huge bottle here. Inside you have opening, then you have rubber cork. You put 2 electrode, okay, and then one probably you just close it. On the other side, you connect 2 chrome nickel wires, okay, and then you just put that into the lower opening, okay, like this. Nickel electrode, okay, and you close it here. You close this, and the chrome nickel wire, okay. Electrically, they are connected like this, okay. So basically, voltage is provided and current is flowing, and this current and voltage electrical energy is converted into heat and heat the air inside the system. Okay, then use power source which gives the value of digital counter 5 volt, okay. I'm not sure, the voltage can vary depending on your system, so probably I would say it will give a constant voltage, okay. A constant voltage. So in our equation, we use the symbol E, capital E. The unit for voltage is V generally, but for the voltage, for the energy provided, the potential energy we provide, the electrical potential we provide, we use the symbol E previously. Connect the precision manometer to the bottle with a piece of tubing. So I showed you the experimental setup where I connect the manometer, which measures the pressure into the system. Now determine time difference delta T. The range of delta T is from 0.1 to 1 second, about 10 values. So you provide electrical current for 0.1 sec, okay, and then measure delta P. Full down, you provide delta T with 0.2 sec, okay, and then measure delta P. You do that like 10 times with different delta T values, 10 different delta T values. But I mean, it is given that the delta T value should be from 0.1 to 1 second, but that depends on your experimental environment and system. How your wire is connected can change actually this delta T value for appropriate experimental procedure for your experiment. So I mean, you have to find the optimum delta T values by yourself in your experiment. So it could be longer than 1 second. Press the start button and measure the pressure. After the measurement, we have to measure the voltage and current, what we used during the experiment. So the voltage and current, it is a constant during an experiment. So you press the button, then you apply the voltage and current with given values, okay, and then you stop. Then you measure delta T, okay, and then for that delta T, you measure delta P using manometer, right? So then we go to delta P. CP bar measurement. How we do that? So replace the manometer with 2 gas syringes which are connected to the bottle by a 3-way stopper. I think I already mentioned about this. So we don't need actually three-way stopcock, but we only need actually two-way stopcock. One of the gas syringes mounted horizontally and the other positioned vertically with its plunger oriented downward. Attach a metal plate to the vertical syringe to increase the weight. Spin the the plunger several times before the measurement in order to minimize the static friction between the plunger and the body of the syringe. Okay. It is actually describing this part of the experimental setup. Now, what is actually here given in the experimental procedure is that, in principle, you have to make the horizontal part, but we are not going to use that part, so it doesn't matter. We are not going to use that part, so you can ignore actually procedure related to this part. Okay, and now you have the syringe here, and then you have to put metal plate here in order to increase the weight. Okay, and then you have to make sure that, I mean, this is a syringe, okay? If you have a cylinder and a syringe, you should be able to smoothly move up and down so that when volume increase takes place, then it smoothly moves down, okay? So there is no static friction. So you have to make sure that it actually moves up and down smoothly. You have a cylinder and fringe. I mean, that part is moving up and down. And during upward and downward movement, I mean, you have to make sure that there is no static friction, which hinders actually the volume change under constant pressure. Okay. So that is actually what are described here. So determine about 10 values again here, 10 values of delta T. And then press button of the digital counter to add heat into the bottle and measure the change of the volume. In this case, you you measure the change of the volume. In the previous experiment, you measure the pressure change with a given delta T by using manometer. Here, you determine the volume change. So separately measure the current and voltage used in each experiment. I mean, in principle, that value should be constant, but I mean, that can vary, I mean, in reality, depending on, I mean, from experiment to experiment. So for each experiment, you have to then record the current and voltage. I think you can discuss many things with your teaching assistant in the real experiment. So perform the measurement again, at least 10 times. So for different 10 delta T values, measure 10 delta P for determining CV bar. Also for determining CP bar, measure 10 different delta V's for 10 different delta T's. Okay. So isobaric condition, CP bar, but P is constant, right? So you have this kind of data set, you will get this as raw data. This will be your raw data. You have 10 different delta T values, 10 different delta V values, okay? And then what you are doing is then you plot actually your delta T on the x-axis, delta T on the x-axis, delta V on the y-axis, okay? Then you will have probably 10 different points like that. And then you draw a single straight line, which actually passes through the data point with the least deviation. Okay. So when you draw a straight line, then from the slope value, you can make inverse of the slope, then you can determine this one, right? So from this plot, this is determined rest, all constant. So you can determine this one. On the isochoric condition, when volume is constant, then you have to be able to measure, actually, you have to be able to get this. And now, experimentally, what you have to do is this. Your raw data will be 10 consists, your raw data set will consist of 10 different delta T values and 10 different delta P values, each delta P for each delta T, right? And then you have delta t and delta p on x and y axis, okay? And then again from the slope, and if you make the inverse of the slope, then you will be able to determine this one, okay? The rest, all the rest are the constants, so you can determine CV bar value. So, okay, so you have delta t here, you have delta p here, your slope, you have probably 10 data point in your with your raw data. You will make then a straight line which passes your data point with the least deviation. Then you will be able to find the delta p over delta p value. Then that value can be used here, and then you will be able to determine the CV bar value. Okay. Torsions. Friction of the syringe has to be low. Okay, the static friction I already mentioned about. At least 10 measurement, 10 delta T values for delta V experiment, and also 10 different delta T values for delta P experiment. So volume of the vertical syringe should be returned as the same as the first condition in every measurement in isobaric condition. So you provide heat with delta T, a given delta T, volume is increased, okay? You move it back, okay, to the original volume, and then measure with a second delta T value, and then volume will be increased, and then you move it back, okay, and then measure the third one, and so on and so forth, okay? This would be reason for setting two syringes in a different way, but without setting two different syringes, we can actually do that. We can actually do that by just leaving one aperture open. So, I mean, your TA will explain about this in detail. So we can control the volume of vertical syringe using the other one. But I mean, this is in principle, this should be like this, but without the second syringe, which is horizontally located, we are not going to use that, but still we can actually make this procedure. During the measurement, only vertical syringe cork is open for isobaric experiment. So I think this is also not that, this is also valid for, okay, so I mean, when you have your a huge flask, and of course your volume change, I mean, this aperture should be closed, and volume change should fully be reflected to the downward movement of your cylinder plunger. Okay, so and then you can open this part, and then you can move it back, close, and then do next experiment. So these are references. Okay, that's it for the first experiment. So next week we will see with the second experiment.